Today we're going to be talking about the different UV curing technologies that are available and going through them so that really to try to give you an idea of the different technologies available and see what would be best for your application. I think before we can really understand what the best technology is for any application, I think it's always best to give a bit of an overview on the application itself. So when we look at UV curing and some of the benefits that you get from UV curing, people are choosing this technology in general for things like the instant cure, when they want to speed up their process time. The UV curing provides cure-on-demand capabilities for parts that need an alignment. The curing doesn't start until the parts are exposed to the light, so it allows two parts to be lined up and then cured nearly instantly. There's definitely some energy savings when you compare UV to various technologies such as heat cure, and also environmental considerations. So UV curing is considered a green application because the adhesives, the coatings, and inks that are used for UV curing are very low in solvents, so they have very low in volatile organic compounds and are considered to be a green technology. So we are finding more and more that has become a consideration for people, where the environmental aspect or the energy savings is something people are looking at UV to bring to their manufacturing process. A quick overview on how the UV adhesive process goes through. And so what happens is you utilize a light to activate a photoinitiator. It starts the curing process. The important point is that you need to have enough light, and that light needs to be of the correct wavelength, and that's something we're going to talk about today, the importance of matching the wavelength of light to the photoinitiator. And once the photoinitiator absorbs a sufficient amount of light of the correct wavelength, then it starts the curing reaction. Then it's just a question of how much energy is then now added to the adhesive or the coating in order to achieve the required level of cure. And this is something, again, as we work with customers, for some applications, people are looking for a complete or 100% cure. For other applications, they don't require 100% cure. It really is all dependent upon on your application and what you need. And so that is really going to be up to the process designer to set the amount of light that's required to bring the adhesive or the ink or coating to a level that's acceptable for their process. Once enough light has been provided and the reaction is complete, then in this case, the liquid adhesive is turned into a solid plastic. One of the things we try to really stress with the customers we work with is that the final physical properties of the adhesive or of the plastic that's being generated by the curing process is critical to the success of their parts. And what we have shown over the last number of years is that the way that you cure an adhesive can have a very significant effect upon the physical properties of the cured adhesive in this case, so of your cured material. So things like the adhesion or the flexibility or even the bond strength can be affected depending upon how you cure it. So you could take the same adhesive, cure it 4 different ways, and end up with 4 different physical properties. So it's very critical that up front in your process you define the physical properties that are required, and then that's going to allow you to set up a curing process utilizing the best technology but also the best design so that your end parts have the physical properties that you need. So if we look at the UV curing process and the variables that are involved and things that need to be considered, certainly there's the adhesive types. So there's different, you have free radical adhesives, cationic adhesives, silicone-based adhesives, all with slightly different properties, and some have different requirements for curing. So it's important that in any process you're working with your adhesive supplier. As I mentioned, we work with all the major adhesive suppliers as far as testing our equipment with their adhesives, making sure that there's compatibility. So that's a customer support service that we provide. But it's important that you understand the curing requirements of the adhesive that you're using for your process. Another important thing to keep in mind, and one of the things that I often find people may not consider, is the materials that are being bonded. So obviously if you're curing an adhesive, if you are curing between two materials, the materials need to transmit the light in order to get to the adhesive. And often what we find is people aren't considering the transmission of those parts as far as the curing process. And so that's, again, that's a critical part of it, something we'll talk about. So whether you're working with plastic parts, glass parts, whether those parts have some sort of color or dye, certainly when you're working with inks, the pigmentation of the material can have a significant impact on the success of the cure, and can also now impact on what technology is going to make more sense for you to use in your curing process. Other things to keep in mind are, as far as the design of the joint, what's the size of the bond? How large an area do you need to cover? Is it a spot that's 1 or 2 millimeters? Is it an inch wide? Is it a large 12-inch display? So the size of the bond that needs to be covered, the speed that you need to do your process, these are all very important. Another thing to consider is exposure of the adhesive to air. And so adhesives will, and the reaction can be very different if it's between two parts where the adhesive is not being exposed to the atmosphere, versus if the adhesive is sitting out and exposed. And I'll go into that in more detail in something we call oxygen inhibition, which again is something that needs to be considered when you're choosing the right technology for your curing process. The process design, so how are the parts going to be fixtured? How accessible is the bond line for getting light to it? Again, different technologies allow different flexibility in bringing light to the adhesive bond line. And so that's going to be a consideration. Is the process going to be manual? Is it going to be automated, semi-automated? And what types of information do you need back from the curing system in order for you to be successful in your process? And then one of the things I'd like to talk about as well is certainly when we look at things like spot curing, we're typically looking at a static cure where the parts are held in a fixture for a certain exposure time. What we're seeing now is as people are trying to increase their throughput and different technologies are becoming available, different UV systems, some of these processes where the parts had been held static are now being done in a continuous curing process where the parts are no longer standing still but are actually moving in front of the UV light source. And again, that requires a very different technology in order for you to do that. And so again, if that's something to consider in your process, if you are looking to potentially increase the throughput, then this may be something that might be of interest. And then the last thing, and certainly from our standpoint, one of the key variables in any curing process are the curing conditions. And these are the factors that are controlled by the light source. And so when you're programming a specific cure sequence, these are the things that need to be understood and need to be controlled. Things like the exposure duration, how long will the parts see the UV light, your radiance level, how much irradiance is being provided to the adhesive or the inks. Spectral content, what are the wavelengths of light being provided? And this is a very key aspect when we start to look at the differences between lamp and LED systems. They have very different spectral contents. And so this is, again, something that needs to be considered. And the last point is heat. And this is something that is a byproduct of the cure process. And so the curing of the adhesives. This is an exothermic process. You're also potentially providing heat to your parts through your light source, through the absorption of light, through the spectrum of light. And so, again, depending upon your parts, heat can be a benefit. Heat certainly helps to speed up the curing process. But depending if your parts are sensitive to heat, then this is something that needs to be managed as well, and needs to be a consideration as you set up your process on what is an acceptable amount of heat, what's an acceptable temperature level within your curing process. So as we go forward, again, the first thing we talked about from a cure conditions was the irradiance. And so if we define irradiance, that's as the radiant power arriving at a surface. And this is really defined as the amount of light being absorbed by the parts. And so in many cases, the amount of light that your parts are seeing can be very different from the amount of light that your light source is sending out. And so things like, again, the absorption or transmission of light through the parts, the working distance that you're working at, because the lights are like a point source, so as you increase your working distance, the irradiance is significantly decreased. So these are considerations where you need to understand the irradiance that is getting to your parts. And more than that, we need to understand the effective irradiance. So we need to understand the amount of energy in the specified wavelength range that is getting to your parts. And so if you look at the charts to the right, these charts are showing the absorption curves for a couple of typical photo initiators. And so it's critical that you match the absorption requirements of your photo initiator to the spectral output of your light source. And then you need to have a sufficient amount of energy to start that curing reaction. One thing to keep in mind, and again, something it's often not considered in a curing process, is that while you do need a minimum irradiance to start the process, there can be a maximum irradiance level that needs to be determined as well, because it is possible to cure an adhesive too quickly, to provide too much irradiance that you can start to have negative effects on the physical properties of the adhesive. You can start to yellow the adhesive, you can start to end up with brittle adhesive, all these things where, again, if you start to provide too high in a irradiance level, it can have a detrimental effect. So what you need to do is you need to find what we call the process window for the irradiance level. And again, this is done through testing, where as you provide an increasing amount of irradiance, what you start to see is whatever physical property you're testing against, whether that be the hardness of the adhesive or the bond strength, as you increase the amount of cure of the adhesive, you start to improve upon that physical property. So in this curve here, what we see is that as we increase the irradiance up to about 30%, we start to get benefit in the physical property of the adhesive. At about 35%, we start to really peak out. We've hit the maximum of this particular property. And so for this example, we've set the minimum irradiance level at about, say, at about 45% relative irradiance setting. So what this does is this gives us a little bit of a buffer between what the minimum acceptable level is and what our setting is. But then you'll see as we go above about 80% irradiance, we start to get a negative effect in the adhesive. And this could be the fact that the adhesive starts to get brittle from overcure, or the adhesive starts to get discolored. And so again, we've set a maximum level for our irradiance. And so this is what we call the process window, and this is really what needs to be established for every curing process. And so if we talk about the irradiance level required, I think what makes sense now is to really talk about the irradiance level or the energy that's available from the different light source technologies that are available. And so what we're going to talk about today, the first one we'll look at is an LED spot curing source. So a typical LED spot curing source will provide about 10 watts per centimeter squared of irradiance. But one thing to look at is the spot size is very small. And so what happens is that you take the LED and you use lenses to focus that light to get a very small spot to get a fairly high peak irradiance. And so 10 watts per centimeter squared is, for almost any application, will be significant irradiance or sufficient irradiance to provide a cure of the adhesive, but you're limited to a rather small spot size. And so what that equates to is actually quite small optical power. And so the power is when we look at the spot available of only about 2 to 4 millimeters, the optical power is fairly low. The LED spots are available in multiple wavelengths. And so again, when we look at the wavelength requirements of the photoinitiator, there's different options available. Because we're dealing with small spots, again, almost exclusively on an LED spot curing system, you're looking at a static cure where the held to the fixture, and you have an exposure time of anywhere from 10 to 30 seconds to do your curing process. Next, if we start to look at a lamp spot curing system, you can see that the maximum irradiance is significantly higher from the lamp system. And that's, again, that's something we have seen, that although LEDs have made a lot of progress, the lamp systems, and this is using a 200-watt lamps, still have significantly higher irradiance. They allow you to do a larger spot size, so you can go 5 to 10, 12 millimeters, half an inch. Spot size is fairly comfortable for a spot curing system. So what that equates to is you have roughly 10 times the optical power coming from a lamp spot cure system. So again, when you're looking at comparing these technologies, the power available from a lamp spot curing system is still significantly higher than what you'd get from an LED spot curing system. You can get higher irradiance, you can get a larger spot, and the wavelengths are much different. So now, rather than 3 discrete wavelengths available, you have a very broad spectrum of 200 to 250 to 600 nanometers. Now again, because you're typically talking a fairly small spot size, these are generally static cure processes again. And the third thing we're going to look at is something that's fairly new for Omnicure, something we brought out recently, which is LED area curing systems. And so again, if we look at the max irradiance of these LED area curing systems, it's about 8 watts per square centimeter. So again, significantly high maximum irradiance, certainly sufficient for most curing processes. But when you look at the spot size, you're no longer talking a spot system, but you're talking an area. So an area of approximately 25 by 50 or 25 by 75 millimeters for this example. And so now when you start to look at the optical power, because you're talking a much larger area of LEDs, and you're talking about now hundreds of LEDs packed into this area, you're looking at over 100 watts of optical power. Now, these types of systems will, because of the area of power, the area that they provide of such a high irradiance, it starts to give a bit more flexibility on both the size of the bonds that you can address, and you can also start to do what we call continuous curing. So rather than holding the parts static in place, you can actually now start to move the parts in front of the light source, and so your parts are being continuously in motion. And this is one way we're seeing people who are needing to increase the throughput of their process, is that rather than have the parts sit static for 10 or 20 seconds while they're being cured, they're actually moving the parts in front of the light source and having a continuous cure going on. And that's, again, now possible because of the optical power that's available and the size, the area, the exposure area of these new systems. So again, these are the different technologies that we have available, and what we need to look at is, once you have looked at the irradiance level, the only way that you can actually tell what irradiance you're running at is by using a radiometer. And so there's a number of different radiometers available, but one thing you need to keep in mind is that the radiometer technology is very different for the different light source technologies. So the radiometer that you're using for your lamp-based system is very different than the radiometer that you'll be using for your LED-based system, because they're different light sources. They have different spectral content. The other thing we find is that radiometers between different manufacturers can be very different, and that has to do with the calibration of those radiometers. And so certainly when you're looking to start your process, you're going to want to make sure that you have a radiometer first and foremost, because if you can't measure the irradiance level of your process, then you really have no control over your process. You want to make sure that you have a radiometer that is traceable to a internationally recognized standard, such as NIST. And then this radiometer needs to be used in order to set your irradiance point, and then also to maintain that irradiance point. So again, to have a repeatable process, you need to maintain that irradiance level, and you need to have the correct radiometer to measure the light source technology that you are using. And the reason it's so important to be measuring your irradiance level ongoing is because the output of these light sources will degrade over time. Now, this particular chart here is showing the degradation of a standard 200-watt lamp system. And you can see that the typical output at 3,000 hours, the output has dropped about 40%. So our 200-watt lamp systems can last 3,000 to 4,000 hours. But over that time, your irradiance level is going to be dropping. And so in order to maintain a repeatable process, you need to be maintaining an irradiance level. LED systems, I'll show in a bit more. I would say one of the myths of LED systems is that they don't degrade at all over time. They do degrade, and much like the lamp systems, the most significant degradation occurs in the first few hundred to a couple thousand hours. And so again, it's important for a repeatable process that you have a radiometer available to measure the output. If your irradiance level is varying, then there's the potential that the quality of your parts will also have some variation in. And so one of the technologies that is built into one of our lamp-based systems is called closed-loop feedback technology. And this is a technology that is designed to compensate for the degradation of the lamps. And so if you look at the chart, what you'll see is that the orange line there is what your process would see if you set your process 4 watts per centimeter squared at the start, and then didn't do any monitoring, any maintenance of your process. After 500, 600 hours, you would be now down to about 3 watts per square centimeter. So there would be about a 25% drop in the irradiance to your parts, and that could be causing some significant changes in the cured property of your parts. The closed-loop feedback, what it does is it's actually a little radiometer built into the system, and it's continuously and automatically measuring the output of the lamp. And as the total output of the lamp goes down, it can automatically compensate for that by adjusting the iris within the system, so that what you end up with is the blue line in the chart, where your process is always constantly seeing the same irradiance level. So this is a feature, again, built into the system that allows to automatically compensate for the degradation. But this is something that needs to be considered within your process. And so whether that is lamp or LED, there is going to be degradation of your light source. And so this chart here now shows typical degradation of a 365 nanometer LED light source. So LED systems can have a very large advantage over lamp systems in their potential lifetime. They can last 20,000 hours or more, depending upon the system. The lifetime of the LEDs is really dependent upon two things, and that is how hard they're being driven. So how high you're turning the LEDs on, and then the temperature of the LEDs. So it's critical in any system to maintain an acceptable temperature level of the LEDs, and this is one of the challenges with LED systems, particularly when you start talking of the LED area curing systems where you have hundreds of LEDs packed in a tight space. In order to get that optical power that's required for the process, it becomes a challenge to cool. And what you will see is that if you're not managing both those variables, the lifetime of the LED can actually be shorter than the lamp. And so the graph here, what this shows is the difference in lifetime depending on how hard you're driving the LED. And so for this particular LED, if you started at 100%, the red line on the chart, you'll see that by about 8,000 hours, it's down to 60% output. So while that's still better than what we were seeing for the lamp system, it's not nearly as good as what we would potentially be expecting from an LED. On the other hand, if you're able to set your process where you only require running the lamp, or running the LED, sorry, at 75% output, you can see it's a much shallower degradation curve there. And now you're starting to get out to your 20,000 hours of lifetime from your LED. So while the LEDs can potentially provide some significant advantage, it really is still dependent upon the process that you set and maximizing the lifetimes of the LEDs to get that benefit. The other thing that is really important to note with LEDs, we talked about the temperature. The temperature has an effect on lifetime. The temperature of the LEDs can also have a significant effect upon the efficiency of the LED and the amount of light that it puts out. So this chart here, what it shows is the output of the LED versus the temperature of the LED. And so you can see at 25% or 25 degrees Celsius, pardon me, or room temperature, the LED is putting out relatively 100% of the intensity. But as the temperature of the LED increases, the efficiency of the LED decreases, so that by the time you're at 85 degrees C, the output on your LED has dropped by 20%. And so again, this is another very important factor to keep in mind, is that you need to be able to maintain the temperature on your LEDs, and your LED system needs to be able to maintain an acceptable temperature, or else, again, you can see changes in your process as the temperature of the LED increases. And so again, that's a feature that we provide, for example, in our LX400, the ability for you to monitor the temperature of the system, so that that's something that you can keep in mind in your process. The next thing we're going to talk about is the spectral content, and this is really one of the biggest differences that you will see between the lamp and the LED. And this chart, I think, is a great illustration of that. So the large blue curve there you'll see is the spectral output of a typical 200-watt mercury lamp. And you can see in this case there's a 320 to 500 nanometer filter. So without that filter there would be energy down to about 250 nanometers. But you can see we have multiple peaks of energy for mercury. We have them at 365, 410, 440 nanometers. The small individual peaks in the middle is the typical LED systems at 365 nanometers, 385 nanometers, and 400 nanometers. So this is a very, very different spectral content between the LED systems and the lamp systems. We talked about the power difference between lamp and LED, and this is an illustration of the spectral difference. So what does that mean to your process? Well, the broad spectrum of the lamp makes it much, much easier when you're trying to match the output of your light source to the absorption of your photoinitiator. Again, if you're working with energy between 250 and 600 nanometers, chances are you're going to find somewhere in there that's going to match up to your photoinitiator. When you start to look at LED and you look at the narrow bandwidth, 10 to 15 nanometer bandwidth, you can see that it's now critical that you understand the requirements of the photoinitiator to match that up with the spectrum of your light source. In some cases, you may not be able to line up the spectrum of your LED with the photoinitiator, and this may limit the adhesive selection that you have. And so again, this is a consideration on the technology that you're going to use. An LED is going to take a bit more work to make sure that you have formulation and adhesive that matches spectral content versus the lamp where you have a much broader spectrum, much easier to match. One of the advantages that the narrow spectrum brings to LED, however, is the fact that if you can match the spectral content of the LED to your photoinitiator, you don't have any wavelengths basically outside of the specified wavelength of the LED. So that makes it much easier to manage unwanted heating of parts from wavelengths that you may not need. So wavelengths that may not be effectively curing your adhesive, they may be absorbed by the parts and can generate unwanted heat. So at the curing process, there's definitely some advantages in looking at an LED technology where it's much easier to manage the absorption of the light and much easier to maintain cool temperatures. But when we talk about the spectral content of the light, obviously it's critical to match that to the photoinitiator. But that's not the only thing to consider, as we talked about before. There's other components within the adhesive. You have monomers, you have oligomers that are going to be absorbing light as well. One of the things I really want to talk about is the material and the parts that are being cured, because those parts potentially could be absorbing light as well. And so things like dark materials will absorb visible light. And most plastics are going to absorb below 300 nanometers. And so the chart on the right here shows an example of polycarbonate. And so a native polycarbonate, which transmits almost all of the light above 300 nanometers, would be very good for using any of our LEDs. However, if you start to look at the stabilized polycarbonate, it now blocks pretty much all light below 400 nanometers. And so, again, it now becomes critical that you choose the right LED that's going to transmit through the parts to get to your adhesive. And this is one example we had from a customer where their adhesive specified 365 nanometers. However, their parts, you could see, had much higher absorption at 365 nanometers than they did at 400 nanometers. And so, although they were trying to use 365 nanometer LED to cure their parts, what they found was, because the parts were actually absorbing a significant amount of the light, they got better results using a 400 nanometer light. If you look at a lamp system, again, you would have a very high peak at the 365 nanometer wavelength. That energy is going to be absorbed by the parts and is going to cause some heating. So these are things to consider, is that transition of your parts is going to have a significant effect on what technology best to use is going to be. Now, of course, with lamp systems, we do have things like filters available, and these give you an idea of the different filter options that are available for the lamps so that you can block out the unwanted wavelengths. And so, again, if there's different wavelengths that may not be beneficial to your process, you can put filters in the lamp systems that will block out those wavelengths. The thing to keep in mind is that as you're adding filters to the lamp, you're actually now reducing the amount of power that's getting through, and so the amount of power that's available for curing. And so what this chart shows is that as you're reducing your spectral content, you're reducing your power, and you can see all the way down, if you're just looking, for example, at 365 nanometers, you can take a lamp system, put in a 365 nanometer filter, and you're basically eliminating 80% of the energy of the lamp. And so you start to look at whether or not it now makes sense to look at a lamp system or an LED system where all you're generating is 365 nanometers. And so even though the lamp may start out with a lot more power, if you're filtering that power out, it may not be the best technology for your process. Another thing to keep in mind, and I think one of the things that can be very important when looking at your process, and we work with our customers a lot on this, is the surface finish, or things what we see on some adhesives that are exposed to the air is a tacky surface. And this is from a process we call oxygen inhibition, where the oxygen will actually bond with the radical and prevent the adhesive from getting that nice hard surface finish. Now, there are different formulations available to improve this, but there's also different ways within your curing process that you can help to minimize this surface tackiness. One of the common ways is people will use a nitrogen purge, so they replace the oxygen in the atmosphere around the adhesive with nitrogen. Another common way is using short wavelength UV, so UVC and UVB. You can see that's light in these wavelengths here. So this the spectral output here is again is a typical 200-watt lamp where we have energy all the way down to 250 nanometers. One of the limitations that we have with LEDs is length commercially available is 365 nanometers. And if we put the 365 nanometer curve, you'll see that we don't get the UVC, the UVB wavelengths that can often help to improve the surface finish of your adhesive. So again, if this becomes an issue with your process, this may be a consideration on the technology that you choose if the short wavelength UV is going to be of benefit to your process. And other things that can be used to help the surface finish are things like high peak irradiance. A little bit of heat can help to give you a nice, smooth surface finish. We talked about environmental, and we're seeing this more often as a consideration. It is not always or not often the major consideration on choosing a technology, but more and more we are seeing people look at bringing in environmentally friendly technologies. Certainly reducing energy has definite cost benefits, but also just overall green environmental benefits, and these are areas where there can be some very significant benefits to LED. The amount of power required to drive an LED system is much lower than a typical lamp system. There's no ozone emissions, which are generated from light below about 220 nanometers, so you don't get any ozone emissions from LEDs. There's no mercury, and there's very few consumable items. So again, as people are starting to look at what is a more environmentally friendly technology, this is again a consideration of people looking at LED technologies. And then sort of the last thing I want to look at as far as the different technologies is we have talked a bit about there's spot curing systems and there's area curing systems. And what we've seen is traditionally there has been some applications for each, and this is just a partial list. It's not an exhaustive list of applications. But what we're seeing is there's applications that have been traditionally done by spot curing, applications that have been traditionally done by area curing systems, and we're starting to see some of these merge in the middle, where we're having the potential of spot curing applications. People are looking at area curing to improve their throughput. You're also seeing cases where people are using both spot and area curing in the same application. And so, again, depending upon what's required, it's important to look at the different options available, whether or not it's just a small spot of energy that you need, or whether there's some benefit from looking at a larger area, a larger array of LEDs that are also available. They're available in higher radiance that is going to allow you to potentially increase the throughput of your process. And so if we're going to start to really look at the comparison of the lamp and the LEDs, we've been through most of these. This is really just a recap of what we've talked about. You have things like an arc lamp system that will automatically maintain the output. This feature is not available in LEDs. The LEDs have certainly benefited as far as things like the lamp hours, the energy required, the lack of mercury is the benefit of an LED. The lamp, you have higher power. With a lamp system, the broad spectrum provides a definite benefit when you're looking at matching up the spectrum of your light source versus your adhesive. The narrow spectrum of the LED makes it much more critical that you work closely with the adhesive manufacturer to make sure that the wavelengths you're supplying match up to the wavelengths requirement. And again, that may provide a bit of a limitation in the adhesives that are required, because if you can't match that spectrum of light with the requirements of your adhesive, then you're just not going to have a successful cure. So what I'm going to just quickly do is we've talked about the requirements in choosing the technology in your process. I'm going to take the last few minutes before I start to take questions and just give a quick overview of some of the specific curing systems that Omnicure has for each of these different technologies. And so if we look at an area curing system, again, what we're seeing is these systems are available that allow you to do continuous curing. They allow for curing of larger areas. So if you have a larger bond area that needs to be cured, area systems allow you to do that. Also looking at things like printing applications where this is always being done in a continuous motion application. They really require the higher optical power that's provided by an area curing system. So we have a couple of different product lines that are available. We have a 7 series LED area curing system. You can see the irradiance levels there are about 5 watts per square centimeter. These systems you can join, so they're available in 6 and 12 inch, but you can actually join the systems up while maintaining the same uniformity at the joint between the two systems that allows you to get really as large an area as you require. So when you start talking about display bonding, you can do anything from a tablet display up to a large screen TV because of this type of array technology. We also have the different small area LED systems that are 2 and 3 inch arrays. One of the things you'll see is that you're now able to get higher irradiance with these, up to 8 watts per square centimeter. All of these systems are air-cooled, and they maintain, again, we talked about the importance of maintaining a temperature that's not going to degrade your LEDs, and these are all air-cooled systems that are capable of running continuously, and they maintain running temperatures that will provide you with 20,000 hours plus of lifetime. And then we talked about the area curing systems allow you to start running a curing operation. And so there's things like conveyors that are, again, can be a tool for you to use to increase the throughput of your system. We talked about lamp-based spot curing systems. For these, Omnicure has what we call our S curing systems. So we have technology built in, such as IntelliLamp, that helps to extend the lifetime of your lamp. We talked about the ability to install bandpass filters. So if you want to selectively remove some wavelengths, these are also available. We have different levels of lamp-based systems depending upon the feature set that you're required. Our S2000 is our most common lamp-based spot curing system. And that has the feature that we talked about earlier, the closed-loop feedback, which will automatically monitor and maintain a constant output. So once you've set the irradiance for your process, the closed-loop feedback is going to maintain that irradiance for you over the duration of your process. With the lamp-based systems, you need to bring the light from the lamp to your parts. And so for these, there are different light guides that are available. There are, again, different technologies available. There's liquid light guides, a very cost-effective way of bringing the light to the parts. You also have things called high-power fiber light guides for multi-legged applications. And these allow you to bring an equal amount of light through multiple legs. So if you need to shine at multiple areas on your parts, there's technologies that are available for that as well. And then some different optical accessories. So again, If you're looking to customize the shape of the light going to your parts, there's accessories available that allow you to do larger areas, that allow you to do rings or lines as well from your spot-based system. And then the last technology we talked about was the LED spot curing system. And for this, we have what's called our LX400 system. It's available in 365, 385, and 400 nanometers. These systems, you can control up to 4 heads independently. Again, you can set specific irradiance levels at each and control each one independent. You can see there's different irradiance, maximum irradiance level available depending upon the wavelength you choose. And you can mix and match the wavelengths as well on the same controller. Again, there's accessories that allow you to customize the spot size of the LED. And we have things like mounting clamps. Again, these things are very important for maintaining the temperature of your LED. As we talked about, that's how you need to maintain the temperature to maintain a constant output. And the last thing we'll leave is with the radiometers. So again, I talked about the fact that the different technologies, the different light sources do require different radiometer technologies. So we have different radiometers available for our lamp-based spot curing system, for our LED-based spot curing systems, and also for the LED-based area curing systems. And so it's important that you have the right radiometer technology to be able to accurately monitor and measure output of your light source. And then this is a little bit about Omnicure, but with that, I'm going to end the formal presentation. Again, the last thing I'm going to leave you with is that as our Omnicure systems, we've been in the UV curing market for over 30 years. We have some specific technologies available in both lamp and LED. So we are able to provide a somewhat unbiased opinion on the different technologies, the benefits, the limitations of these technologies, and which might be best for your application. We also have testing facilities here within our house that will provide some support, again, if you're looking at actually doing some material testing with the different technologies. We have that capability as well. And with that, I'm going to open it up to any questions. And so if you have questions at this time, please send them through the chat. And so I have a question from Bob Burbank, who has asked whether the spectral output of a 85 LED varies as it ages. What we have found with the LEDs is that they maintain a very stable spectrum as they degrade. So the output level, so the peak stays almost constant at 385 nanometers. The speed at which it ages is very similar to the chart I showed on the 365. So again, from a 385 nanometer LED, we would expect a very similar lifetime as the chart 65. Starting at about 75% output, we would expect to get easily 20,000 hours of output. So thanks for that question. Is there any other questions? We're open up for any questions now. Oh, I got another question. So how do we know the optimal wavelength of the adhesive photoinitiator? Such information is not always available from the adhesive supplier. And that's a great question because, yes, that's one of the troubling things we run into a lot is trying to get the specific absorption curve of the adhesives being used. A lot of times in the spec sheets, the adhesive suppliers will provide you with the light source they use to cure the adhesive, often a lamp-based system, and they may specify a wavelength. But what you will see is that it's very difficult to get the information on what the optimal wavelength or the optimal absorption. And there's a couple of things I'm going to talk about on this one. Is one, you don't need to match the LED with the optimal absorption of the photoinitiator. All you need to do is match the absorption curve of the photoinitiator with the output of the LED, and you need to have sufficient amount of match in order to activate the photoinitiator. I would say on most of the photoinitiators that are being used today, and certainly the ones that we have experience in using, we have very good success using 365 nanometer LEDs. We often have very good success using 400 nanometer LEDs. These are not the optimal absorption peak for the photoinitiator. The optimal absorption peak is often down in the 250 nanometer range. But what you require is you require sufficient energy in the absorption range to get the cure process started. And so that's, it's a great question, because it's not a question of matching the optimum absorption peak of the adhesive. It's just a question of having enough of an overlap that there's sufficient energy to drive the curing process. One of the things you'll also see is that typically your 400 nanometers LED will have double or more the output power of a 365 nanometer LED, for example. And so what we see, some photoinitiators, while they'll have higher absorption at 365, the extra power of the 400 nanometer will actually provide a faster cure. And so it's critical that you match the absorption of the photoinitiator with the output of the LED, but you don't have to make it the optimal wavelength of the LED. So hopefully I answered that question. Another question on how do we control overcure of the adhesive? Well, overcure of the adhesive is really going to be dependent upon the physical properties that you're looking for in your adhesive. And so, for example, if you're curing an optical adhesive, where one of the critical pieces is that the transmission of light through the adhesive is 99% or better, then one of the things that can happen if you overcure your adhesives is that you start to yellow. And you can test for that during your process setup by doing tests at different irradiance levels, and at some point you may start to see yellowing of the adhesive, and that's going to tell you your maximum irradiance level. But the maximum is really dependent on the physical properties of the adhesive. So if you cure an adhesive with too high irradiance, you can start the reaction going too quickly. You can start to get, for example, lose flexibility in your adhesive. The adhesive starts to become brittle. The bond strength could actually decrease. So these are things that you can measure while setting up your process window. One of the things that you'll find is that if you're using, for example, a lower irradiance level, and the adhesive may be cured after 10 seconds, and you cure it for 30 seconds, very rarely do you find that that is an issue with the adhesive. Because obviously once the adhesive, if it's cured, and if it's cured in a controlled manner, additional UV probably doesn't have a detrimental effect. What can be more of an issue is that very high irradiance that is being added to the adhesive right away. And that is obviously something that needs to be set up within your process, and we talked about the process window where you're looking for your minimum and maximum irradiance levels. I had another question here that there's two types of adhesives available. I mentioned that during the presentation. So the two most common ones that we run into are what's called free radical adhesives and cationic adhesives, and there's some differences between the two. There's also some silicone-based adhesives. We don't run into those quite as often. Free radical adhesives are adhesives we see them very often on joining plastics. They're very commonly used in medical device manufacturing. In the free radical curing process, as the light generates the free radicals, the photoinitiator is actually used up within the curing process. And so what that means is that at the end of the curing process, the photoinitiator is completely used up. The other thing is that when you're curing, if you remove light from the adhesive, the curing process stops. The photopolymerization process will stop. In a cationic-based adhesive, the photoinitiator is not used up. It actually is regenerated through the curing process, or recycled through the curing process is probably a better description. And one thing with cationics is what you will actually find is that once you start the curing process going, because the photoinitiator is being recycled through the curing, the reaction, removing the light, you'll actually see the cure continue on. And so cationic adhesives can actually allow you to get things what's called shadow cure, where if you have parts where you're maybe not able to get light to all parts of the adhesive, as long as you can get light to a sufficient amount of the adhesive, you can start the reaction going, and over time may be able to get some curing of the adhesive in parts that are shadowed by the light. Some of the other differences, free radicals will typically cure faster than cationics. Cationics tend to have better environmental resistance than free radicals. I mentioned free radicals have great compatibility with plastics. Cationics, a lot of them can be used with plastics, but they don't have the same compatibility. The other significant factor we see certainly in when looking at the different light sources, and this is a generalization, but what we've seen is that free radical adhesives tend to cure very well with LEDs, and LEDs up to 400 nanometers and even a bit higher cure very nicely with the free radicals. The cationic materials almost exclusively will require 365 nanometer light. So most of the photoinitiators used in cationic adhesives, the absorption above about 375, 380 nanometers is almost nil, and so they do require 365 nanometer LEDs. Again, if you're looking at a lamp system where you have broad-based, then both materials are relatively equal because you have wavelengths that will be compatible with all materials. When looking at the uniformity of the LED area cures plus or minus 10%, how small a spot size is used and at what distance? Okay, so for our area curing systems, when we look at the area, the exposure areas that are available, whether that be a 2-inch, 3-inch, or 6-inch, we have, depending on the working distance, the actual area that is within the plus or minus 10% will vary depending upon the working distance. And so when we give our specifications of the exposure area, we will give that depending upon the working distance. And so, for example, at 5 millimeters, even though the LED exposure area may be 75 millimeters, at 5 millimeters you're down to about 70 millimeters that falls within that plus or minus 10% uniformity. But we give those specifications with the systems, and so as you're looking to select the system that's going to provide enough of an area within that plus or minus 10% exposure area, that's the data we would provide, and it really depends upon the system. With all of our area curing systems, we also provide an optic in front of the LEDs that allows us to maintain that uniformity at longer working distances. And so, for example, if you have some restrictions in your working distances, we can look at different optics that are available that will help to optimize the output, optimize the working area, potentially optimize the irradiance level, depending upon your application. So all of our area curing systems, again, we put a lens and optic in front so that we have the ability to really almost customize the light for your requirements. So That uniformity will depend really upon the working distance, but also on the optic that is being used with the system. I'm going to take a couple more questions, and I thank you all for your questions. Sorry, so optimization of the cure depends upon the geometry and chemical nature of the material. What happens if parts are very small and the amount of adhesive is minimal? Positioning into the UV spot becomes critical and it's hard to see yellowing due to over-cure. Excuse me, how would you deal with such difficulties? Well, we're starting to get into some specific application processes. So for this question, I'm going to suggest we take this one offline. We can get in touch directly and we can work with you. One of the things that Lumidynamics will do is we do help you in setting up your curing process. As I mentioned before, we will take materials from customers. We can do some testing in-house here. We do have a full materials testing lab in-house. So we can do testing with both our lamp and LED systems and provide you with information on how we are able to cure. And this will give you a starting point. It'll give you some confidence on which light source is going to be successful in your application. We do have a database of testing with adhesives already available in-house from testing we've done with our LED systems already. Again, this helps to show if the LED will be successful, the wavelengths that are required, and this is information that is available to all of our customers. Again, it's part of the support we provide in helping you select the best light source technology for your application. And I'm running over time, but I'm happy to stay and answer questions if they keep coming. I have a question on the heat generated by an area cure LED system. And the question is, and this is a really good question, will the substrate heat up from an LED-based system? And this is, again, when we talk about the heat on the substrate, there's a couple of different ways of heat being generated or heat being transmitted from the curing system. So in a traditional lamp-based linear curing system, you have a lamp that is sitting on top of the substrate. The lamp is generating a significant amount of heat on its own. That heat is being radiated to the substrate. Lamp systems are generating a very broad spectrum of light that runs from below 200 nanometers up and into the infrared, so above 700 nanometers. And so you have a very large portion of the spectrum from a lamp-based system that is generating infrared light that will be heating the substrate. Now, again, there's different ways to filter that, potentially filter that infrared light out, but that is generating heat on your substrate. The other thing, again, as I mentioned, the curing process itself is exothermic, so that's going to be generating heat as well. But the last part is just the light itself, even light that is being absorbed by the adhesive and the photo and the parts. As light is being absorbed by parts, it can also start to heat up the parts. And so when we look at LED systems, you're eliminating a significant number of those factors that are going to be heating up the parts. So with an LED system, the light source itself is cool. So it's the light source itself that is sitting above your parts, sitting above the substrate, is running at 50, 60 degrees Celsius, so it's not radiating heat onto your substrate. There is no infrared light being generated. So again, you're not radiating, you're not sending any infrared light or heat onto your parts. There's no UVC being generated. Again, this is another area where you can have absorption by plastic and get heat. But what you do have is you do have a very large amount of optical energy that is being sent down onto your parts. And that optical energy, if it's absorbed by parts, will convert into heat. And so it is still possible for you to overheat parts using an LED system. And that's one of the one of the misconceptions that's out there with LED systems is that you will not heat your parts at all. The energy being put out, as we saw with those LED area cure systems, is over 100 watts of optical power. So that energy's got to go somewhere. And if it's being absorbed by your parts, it will heat it. If you're using a black conveyor belt that is stopped underneath your LED system and your LED system is on, that black conveyor belt is going to absorb the light and it's going to heat it. And so there still needs to be some care taken. Now, having said that, testing we've done has shown that when you're curing parts at typical speeds of 5 to 8 feet per minute, we are able to cure a number of plastic parts, and we've done a lot of testing for various customers in applications where heat is an issue. And we're able to fully cure the adhesive in their plastic parts and maintain a temperature of below 40 degrees C for the parts. And so again, as long as you're managing the energy of light that's going to your parts, to your adhesive, then you can really manage the temperature. But it is a misnomer to think that you're not going to have any heating of the parts because you're producing such a significant amount of energy that if that's being absorbed at all by your parts, it will be producing some heat. And so hopefully I answered that question. The last question that we've gotten a couple of times is about the presentation. And yes, the presentation will be available. We're going to be emailing out the recording of the webinar here. So we'll be emailing that to everyone who's registered. So you'll be getting that. You can also, you have my contact information here if you want to get in touch with me on any other questions or any other specific parts. Please also go to our website. There's lots of information there. We'll have the webinar posted on our website at ldgi.com. And with that, that is the end of our webinar. We have gone over time, so I thank you for your participation. Thank you for all the questions. And I hope that we provided some good information for you. And again, if there's any more questions, any more information, feel free to visit our website, contact me directly, and I thank you again. Bye.